Can you see my screen? Perfect. Okay. All right. Transition to data mesh. Why and how? So for folks who don't know me, I think I was already introduced, but I head the emerging tech in North America. I also founded the concept of data mesh. I have 2 books. One I have contributed to along with my colleague Neil Ford, Pramod, and good friend Mark Richards on architecture, the hard parts. I have another book coming out this year, Data Mesh. I have left 2 codes for you. If you have access to O'Reilly platform, well, you can access to all of these books. If you don't, that code will give you some free access. And even though the books are not yet ready to buy, I mean, you can pre-order them, but you can read them in a pre-release format, on edited format on O'Reilly platform. So what is data mesh? So data mesh is really a decentralized sociotécnico approach in sharing and managing and accessing data for analytical use cases at scale. So I've got a few words here that maybe I should unpack. One is why I'll call it a sociotécnico, because it is an approach that concerns itself with both the technology in terms of architecture and how we kind of organize the technical pieces that are involved in managing and sharing data for analytics, but it also concerns itself with the relationship of technology with people, the organizational structure, the incentives, the roles, because as we know, if we want to have a solution that really scales out in a complex world, in a complex organization, we can't just think about architecture and forget how that impacts the life of people. So that's why it's called a sociotécnico approach. And I also have another word there, analytical data, and also scale. So what does analytical data mean? Well, it's really a data that serves the data scientists and the data analysts and all of the roles in between the two that are busy building machine learning models. The data is used for machine learning models to find patterns, to discover relationships between the facts that have occurred in the past and explore and exploit those facts in terms of making predictions, in terms of data that you will build reports and do analysis, a trend analysis to also look at the past and see what sort of trends you see and do diagnosis analysis. And as we see, there's a big shift in our industry. We're moving quite a large portion of our technical solutions from building solutions on top of logic, like if and else, like if this happens, do that, and if not, do the other thing. And this kind of imperative programming to data-driven programming with ML models that we are training these essential statistical mathematical models that find patterns in the data and then make predictions. And that's a very different usage, different access model of the data, and that impacts what the data and what the data looks like for those use cases and how it's accessed. It's very different from the data that we put in our application databases, because it needs to have a representation of all the facts across a wide spectrum of time. So all of the facts that have happened in the past and are happening, we need to have access to that kind of temporal view of the data. The data really needs to represent the reality of the business, what is actually happening in the world, as opposed to being perfectly modeled, downstream to a approximation of that reality, right? Because we really want to know what's happening, what are those fine-grained facts, so we can train solutions that we haven't even imagined, right? The difference between, again, the database models that we build today and the analytical data is that database models are serving a very specific application at this point in time. They're keeping the state of transactions that we're performing with our users, right? But for analytical data, we don't even know how we might be using it, because the solutions, the analytical solutions or machine learning models that we would train in future over the data that we're capturing today, they might be looking at signals and facts that we haven't even bothered capturing. So we want this data to be as close to the reality as possible and capture as many facts as we can. And that data can come from anywhere. It doesn't come from one application or the other. It comes from every single touch point that you have with the environment around you, with your customers, and naturally it has a large scale. The other kind of attribute that I talked about is that the data mesh tries to solve the problem of scale. And if you look at the fact, last couple of decades, you might say, well, we've actually solved quite a few problems of scales, and that is true. In the early 2000s, we solved the scale of the volume. We all went on web and started kind of building these web applications that generated a lot of data. And we had to deal with the volume and processing and the parallel processing. And then that's where the kind of the Hadoop world and MapReduce way of parallel processing the data came to exist, or distributed files and so on. And then, we kept expanding our footprint in terms of the types of applications that we were building. And that led to digitization of different types of data, right? So that we had to deal with the scale of variety. So it's not just, structured data, we have unstructured data, we have text and voice and images. And that led to kind of the object storage and be able to store very different, diverse kinds of data. So deal with that scale. And then we went mobile, right? And devices and IoT devices. And we had to deal with the velocity and the speed at which the events were being captured. And that gave birth to the Kafkas of the world and message processing and stream processing approach to analyzing data. So what is left for data mesh to address? And what is left is the reality we live in. We live in a world that is constantly accelerating towards complexity, towards growth. I mean, that's just the foundation of physics, entropy. That's we can't stop. So if we are in a world that organizations are continuously growing, continuously creating new touch points with new types of customers, with new types of applications, with new types of partners, and our aspirations have grown from, a few reports or a few niche kind of data science applications to really try to apply ML to every feature, every workflow, everything we do. And the data can come from anywhere, and that complexity is constantly growing. How do we solve the access to data? And if you look at the architecture today, this is what we're doing, right? We have applications on one side running the business. They have their own databases. Hopefully they have their own databases. They're not sharing any databases with each other. That's we call data on the inside. We have on the right side, the blue side, you've got your lakes and warehouses, and you've got kind of these spaghetti pipelines, complex pipelines going into ETLs and getting data out of these databases, which were never designed to share the data for analytical purposes. I mean, those databases were not, expecting to be invaded by some ETL job to create downstream models for analytics. And the downstream models for analytics, people are always complaining these application developers are not designing their databases correctly. Well, their databases wasn't created or designed for analytics. And then on top of that, we've got some sort of a synchronized and centralized governance that tries to kind of get its arms around the security of this data that we're moving around, the privacy of the data, availability of the data, and so on. And you might say, well, what's wrong with this picture? It seems like quite nice, and I've got colorful, boxes. Look simple on the paper. And I wanted to share a story because I love the work of Joseph Campbell. He was a author, professor of literature. He influenced the Star Wars, and I'm sure there are fans of Star Wars here. But he said everything starts with a story, and the story really, at least for me, started with 2018, where it was an interesting point in time. We saw that a lot of our technologically advanced clients, particularly on the, I'm in the West Coast of US in Silicon Valley. So you can imagine the kind of clients that we get here. They have already invested a lot in their data platforms, migration to clouds. I had all of these aspirations around how this data being used, yet they were coming to us and looking for another solution. They had these symptoms, they had these failure modes. They were failing to scale out to have their warehouses or lakes with satisfying many different consumer use cases or many different sources. They were going from one platform to the next platform and stuck in this bootstrapping. And finally, they were failing to materialize, getting value from all of this investment of building the next generation data platform at scale. So when we looked kind of underneath all of this, there is one characteristic that was common across all of the solutions that we had built, whether they had built a warehouse or a lake house or whatever, the lake house on the cloud. They were, the common characteristics at the organizational level and at the architectural level was that there was this assumption that you have a data team, you have data team under your chief data analytics officer. The job is capture data and cleanse data and organize data and put it in the, from all of these places in the organization, and then satisfy the needs of, kind of all of these innovative solutions that you want to innovate with data, with this central team, with this central technology, with this centralized approach. So, I mean, I pulled a very silly, simple example here, but you can see that this causes a bottleneck. This causes a lot of friction. So if we imagine this purple point is where we are, where the reality sits today, which is we are at the point that the scale is growing, the business complexity, expansion of sources, proliferation of use cases on one hand, and we're looking for a solution that can still allow us to have agility, still allow us to have immunity to change, still allow us to be resilient to data, in fact, being copied from one place to another. Again, I think if we embrace the reality of our physics, which is entropy, data moves around, data gets copied, around, and yet we're trying to put all this energy into our organizations to have one single source of truth, one canonical model, and that just simply doesn't scale. So we needed to really inverse the thinking, come up with a new model that embraces the complexity that we're dealing with, yet we are getting value from data, yet we are respectful of privacy and security and all of the policies, and we can move fast. So data mesh objectives really can be summarized in what I have up there, which is we still want to respond really gracefully to this volatility and complexity of our world. We still want to sustain our agility when we are constantly growing. We don't want a system that slows down as we get more data sources or more use cases. And really, we want to have a system that the more money you put in, at least you get more value out of it. Right now, it feels like we put more money, but we don't really see that kind of exponential or even linear growth of value from it. So data mesh tries to address a lot of blockers. So centralized bottleneck, any centralized bottleneck, let's remove that, right? Let's remove that by some form of decentralization. Let's get the data closer to the source and reality. Let's remove all of this pipeline fragility out of the way. Let's bring in accountability and long-term ownership to the data and treat data as a product. And let's build solutions that can really bring a larger population of our generalist technologies to contribute to this beautiful and really rich space with data and ML. Right now, that space is allocated to a very small population of specialists. So these are some of the kind of goals of the data mesh, and underpinning the solution sits these four pillars, really these four basic principles. I'm going to have a drink of a tea. Maybe I'll go on the last page so you can look at all of this and while I have a little sip. So what are the pillars? At the heart of it is the leftmost pillar, is that we've got to find an axis around which we can decompose our organization, our ownership of the data, the architecture to keep the data so that we can scale out with the growth of our organization. And that's a domain ownership. That's domain-oriented or domain-driven decomposition of data architecture. The second one is we need a model where data sharing, data connectivity is above and beyond any other thing we do. So that's the second one is data as a product to enable data sharing. We need to have an infrastructure that really empowers independent cross-functional teams to use data for innovation or share the data without friction. without needing to hire another 100 data engineers. And that's the new thinking around self-serve data infrastructure. And finally, we need a model of governance that doesn't need to sit in the middle of every data processing value stream and try to stamp and validate every piece of data from manual policy enforcement perspective. So we need to still have those policies and enforce them, but in a more federated and a more automated computational way. So I'm just going to go quickly through each of these and describe a little bit what sits behind it, how it gets implemented. And at the end of the talk, I want to talk a little bit about kind of the transformation towards data mesh. Around 2000, early 2000, 2003, this book came out by Eric Evans, right? Domain-driven design. And the purpose of, if you look at the subtitle of that book, it says tackling complexity in the heart of software. It's interesting, right? In early 2000s, what was happening in the world? We had discovered internet and the power of it, and we were all busy building web applications, right? We just like digitalization started seeing a growth and a complexity in the software that we were building. So the way we were designing software, monolithic softwares, it wasn't really addressing the natural complexity, the organic complexity of the businesses we were building. So he came with a new model that said, okay, if you want to model your software, you can't have a centralized modeling. You can't have this kind of monolithic approach to modeling of your software. You can't also have this siloed, everyone does its own thing, nobody talks to each other, and you can't have no modeling. And if you map this to where we are today, we're going through the same curve of complexity, but in a different place, in a data-driven solutions in the data sharing. So we can't have a warehouse that expects you to have this beautifully designed Snowflake centralized canonical modeling. We can't have application databases, maybe with some virtualization slapped on top of it, do their own siloed modeling without interconnectivity. And we can't have lakes with no intentional modeling behind it. So we need something new. And data mesh takes aspirations from some of these strategic design patterns from DDD, like bounded context. Let's do modeling intentionally for a bounded context of the business, where a business unit aligned with a technology unit has influence on the language, the knowledge, the activities, the particular outcome of the business. And let's define then mapping between, if you're, let's say, a digital streaming business, if in the business of podcast recording and the business of listener registration and the business of artist acquisition, let's come up with ways to actually map these modeling in these different domains to each other, and then use a ubiquitous language with each model, empower each team, each domain to really use their ubiquitous model. So I think we can learn from this and apply this to data. So then what we end up with is a distributed decomposition of the data around domains. So some domains are, if I again take the example of digital streaming, some domains are aligned with the source. So you have player devices, like, your media playing application, then you have player events, and you have domains that are working with those domains that are building those player applications, and also now responsible for a new concept, this data product. And I use this icon of hexagon with lines and kind of those lollipops outside of it as a notation to demonstrate a new concept, new architectural concept, which I'll go into, for sharing data. You have domains that are aggregating, perhaps, like you have your listener profiles that are aggregating information from how the listeners are behaving with your players and what information they provide to you during registration. You have the domains that are more aligned with the use cases. So maybe you're doing some sort of a recommendation based on the social networking and who's friends, who's following whose playlist and what preferences they have. So with this first principle, we really changing our approach from thinking about data needs to go from source to some destination through some pipelines before it gets useful, and really bring that to closer to the source as a new concept of a data product. Have different models that are interconnected, stop putting all our energy to these kind of controls that work against the grain of reality, which is like single source of truth. Let's embrace this idea that data can be in many different places, but we have knowledge about the trustworthiness of the data to decide. We have transparency about that data to decide which source actually, which version of that data we want to trust and use. And finally, instead of decomposing our organizations around technology, because data people know data technology, let's just start organizationally structure ourselves around domain. But as you can imagine, this domain-oriented kind of ownership and architecture can do result in siloing of the data. So then to prevent any siloing of data in these domains and enable interoperability and interconnectivity, and sharing, most importantly, sharing of the data, Data Mesh introduces the second principle of the data as a product. So, which is really an intersection of product thinking and data. And a successful product, based on the work of Marty Kagan in his book Inspired, is something that is usable, is valuable, and is feasible to build. So let's apply what is usable and valuable to a data product. So in this diagram, what I'm showing is that you have your domain. I don't know why I jumped to health insurance, but let's say this is your listener profiles. I'm just using here an insurance example. Like you have your claims, and you have pharmacy claims and medical claims, all of these claims that you hope your insurance will pay you back. In that domain, you have product owner. But those data products, really, for them to be useful, to be valuable to their users, and who are the users? Those people on the right-hand side, data scientists, data analysts, they need to provide data in a shape that is natively accessible to those folks, right? And which means they must provide the same data in multiple formats, in multiple styles, until the day comes that we have one universal mode of accessing data. We have all moved to event processing, but that day is not today. We still have a data scientist that like to access the data with their native tools on a columnar base. So they prefer files, JSON files based on the columns, like formats like Parquet. We still have data scientists that like to run SQL queries. I mean, SQL is not going anywhere, or actually algebraic languages for, performing queries are not going anywhere. So we still have to support that mode of access, perhaps more with a relational structure of the data. And maybe you have, applications that have moved on from these models and they're continuously processing events and they're happy with event processing. So may provide the same data as events. But nevertheless, it is the same data product. And for this data product to be considered a product, it needs to go beyond just a bunch of files on disk or a bunch of tables in a warehouse. It needs to be intrinsically itself, have APIs, have characteristics that make it discoverable, uniquely addressable, have documentation so it can be understood, not simple documentations like a schema, beyond that, showing with perhaps computational notebooks how that data can be accessed, what are the shapes and statistical characteristics of it. It has to be secure, it must be interoperable, so there are aspects to that data that are, maybe some of the field types or identity types that need to be really globally defined, so it's interoperable. It needs to be valuable on its own. It has to have some data that has value to somebody, otherwise we don't bother making these data products. So you might say, okay, this is a lot of a lot of responsibility. We can't think of data no longer as a set of files, right? Or as a kind of a dormant information on disk. And this is where I want to draw from this wonderful concept, architectural quantum, that was initially introduced in the work of my colleagues in the book, Building Evolutionary Architecture. And I think we need to change what we mean by data. We need to come up with a new unit of architecture that has all of the structural elements in a way that it can autonomously address all of those concerns that we had up there. This is a shift that we've had in the past in the operational world. Remember, we went from kind of applications that had so much environmental dependencies. They couldn't do anything without having, all of their environmental dependencies independently managed, to microservices, where we said, okay, microservice and all of its dependencies are managed autonomously. The microservice is responsible for its data, it's responsible for its health status, it's responsible for its APIs, how it gets access. And I think we need to now, with data, come up with a new concept. It's a bit different from a microservice, but it has similarities that it needs to have all of the structured components. So when you think about a data product, I call it a data quantum, the logical architecture unit, it needs to have the data, of course, in access in the multiple modes. It needs to have an articulation of what dependencies it has from the infrastructure, what sort of storage it needs, what sort of retention it expects to have, and so on. So some form of an infrastructure manifest. And it needs to, most importantly, it needs to have code, computation that keeps that data alive. I mean, I cannot think of a single piece of information that won't change, or our understanding of it won't change. So we still need to have that transformation code along with the data, along with our requirements around the infrastructure that will host us as one unit, so that we can satisfy all of those discoverability and so on. So that's characteristics. So let's take it through an example. And I notationally use this hexagon in all of my writings to represent this new definition of data, new architectural components. That when we talk about, you and I will talk about data from now on, we talk about this, not files and disks. And that's why I call it data quantum, so we don't get confused. So let's talk about listener demographics. You have a data product that tells you who the listeners are, what the genders is, ages. Of course, they make sure that privacy is respected. But that data needs to come from somewhere, right? This data product needs to get its source from somewhere. So we will have a set of mechanisms for ingesting, receiving data from either collaborating applications, like in this case, you might have an application that's microservice that's dealing with listener registration, and you decide to have some sort of an event stream that you are exposing the listener registration domain events, and this data product consumes it. You might have another data product in another domain, like that is exposing the historical view of the listeners' sessions, like how the listeners interact with their players. You get those two information, and then you have transformation. In this particular case, the transformation might be actually a classification, machine learning, plus a few other pieces of code to really create this new demographics, a new profile of your listeners. And we need to have storage to actually store that representation in whatever mode is most relevant. And then we will have output, modes of output, so that we can now provide this, remember, temporal. And I would say bitemporal and immutable. And this is a very deep conversation that I won't get to today, but I talk about it in the book. That why I think the data sharing needs to be moving from this kind of constant updates to immutability, with making sure that every piece of data has the time of actual events. Like, okay, this listener demographic information is based on the listener's registration or our understanding of the listener over this period of time. So we need to have this real actual time that this listener information belongs to. And we need to have a time that is representative of when we actually process this information, where we perceive this information, our understanding of that time. So sometimes we call it processing time or transaction time or record time. So we need to have these two times always available, because again, remember, people in the future are going to come and look at this data and try to make sense of it. And these times allow us to really gain trust and understanding, and have also a global consistent view of the data, no matter how many data gets transformed through these data products. And finally, downstream, you will have maybe another data product or another application that uses this data for, let's say they want to decide which outreach they need to have to the listeners, what sort of marketing maybe they want to propose to them, and so on. You need to have discoverability and observability APIs, ways of mechanisms by which you can kind of identify the data product, learn about the semantic of the data, learn about the SLOs and metrics, like how often this data gets updated, what cadence, what's the quality of it, what's the nature of it in terms of completeness, get access to the documentation, get access to all the logs and traces so you can have the lineage of the data. And finally, you need to have another set of controls, mechanisms by which that you can run, you can configure the policies that this data product needs to enforce at every point. Maybe at the time of input, it needs to do access control upstream. So it needs to have a policy that describes its identity and roles and permissions that it has. It needs to apply some policy during transformation. Maybe some of this data need to be secured in memory. So you need to use some sort of a secure enclave for that. The policy that has around the privacy, like who can actually access this data, what data need to be encrypted, anonymized, or not even presented. So we need to have a way of encoding these policies as computation, as code into each and every data product. So at the right moments of access or transformation or read or write, those policies can be enforced. And also any administrative kind of eviction of the, let's say, a particular record, administrative functions and controls we might need to have. So this is what I think we need. This is what I propose as the architecture of when we talk about data from now on. This is what we're talking about. So it's not just a bunch of files and disk anymore. And that really gives us this transformation from, oh, data is an asset, is files we've locked up in, disk somewhere, and to data as a product is lively. It's not a byproduct of running the business, but it's a product in itself. It's not an output of some source code we dump. It actually contains the code that maintains it. And at this point, you might say, okay, now we have a lot of requirements for this. So we've got to empower our teams to be able to actually do this. Like we're asking cross-functional teams with data product ownership, data product developers, and application developers to now share data, to use data. So what sort of infrastructure do we need? And we need to really rethink our platform thinking. And our platforms are really the job of a platform. The definition of a platform is really to reduce the cognitive load of their users. In this case, data product developers or data product owners, data product consumers, reduce their cognitive load so that they can do their job without friction more easily. And in this case, we need to reduce the cognitive load of these folks, data product developers, data product consumers, data analysts, data scientists. So we need to have a kind of a platform that really embraces these as the first-class citizens and provides a set of interfaces. So if you think about the interfaces you have today, we have these utilities, right? We have storage, we have workflow orchestration, we have access control, right? You have the airflows, prefix, you have your lake storage, your object storage. Great, we've got all of that. What we need is really a new kind of set of new layers of the platform that focus on the experience and the experience of these developers. Sorry, I need to go back a little bit, this jumped up. So if we say that this data quantum is the unit of exchange of value now, this is the thing we build, this is the thing we deploy, this is the thing we use, then we need to have a new language, a new set of tools for creating it, for deploying it, for versioning it, for setting privacy on it. So the platform needs to now speak a new language with us. That's a higher level of abstraction. And finally, we're not talking about one of these data products. We're talking about a mesh of interconnected data products. So then there is a set of functionality that we need to provide to experience the mesh as a whole and not just a single data product. And that's search, that's discovery, that's browsing the mesh, that's looking at the lineage graph between the data flow, between the data products. We're looking at the knowledge graph, the link between the data product data models, right? How the listener data model is actually linked, listener demographic, maybe to a listener record to a listener. So these are the capabilities that platforms need to provide to us. And there's not one platform per layer or one solution per layer. These are all independent, kind of tools, hopefully independent tools. So you have a bit of a, freedom and power in terms of the not getting locked into one vendor or another, but different tools that play nicely together to provide these experiences. So let's go through one quick experience of a data product developer. I come and incept and explore and bootstrap a data product and then test and deploy and monitor and maintain it and evolve it. So for all of these, I need a set of capabilities. I need to be able to search the mesh to see what data products do I have. I need to be able to connect to one, start querying data. Is listener registration give me the information I need? Do the listener session give me the information I need? I need to quickly initialize a standardized kind of blueprint of my data product with some scaffolding, so I don't have to build everything from scratch. And then I need to really focus on what matters, which is building the transformation and make sure the data that I'm generating has the integrity and has the guarantees that I'm claiming, right? So the change between the platforms that we have today and the platforms of the future are really, if I want to pick one of these, is that we need to satisfy cross-functional teams. We don't need to just satisfy specialists. We need to satisfy the needs of our generalist technologies to be able to scale, to really have data-driven solutions. And instead of thinking about mechanisms, think about experiences that we need to empower. And finally, the last pillar really is around how do we make sure that with all of this complexity of different teams building data products, making sure these data products interconnect, making sure the security, privacy, all of those goals are in place, making sure the teams are actually engaging with each other. And that comes to automated federated governance. And in this model, really, the job of the governance remains the same. The objective is getting, one of my colleagues famously said that getting the right data to the right person at the right time, right? So we still want to embrace that, but we want to deploy it very differently, approach it very differently. So we want to find this equilibrium between centralization, right? We need to have standards that are still the same to allow one data product to talk to another data product, but we need to also embrace decentralization of domains, that we will have different teams at the same time building their own data products, right? So the characteristics of this computational governance is really that the things you need to embrace is that we have to come up with a set of standards that can be coded, that can be computationally automated and implemented by the platform. We have to embrace that this is a very dynamic topology. We can't put a person in the middle, try to orchestrate the work. So it has to be really addressing this kind of dynamism that it has. It has to embrace interoperability, decentralization. So there's an operational model that Data Mesh talks about around bringing kind of domain teams, domain product owners who are accountable for these data products involved as a federated team in making decisions, incentivizing them, both with local incentives in their domains, but also global incentives in terms of the mesh as a whole to operate. Have SMEs, of course, available to that, have a set of principles that guide the decisions they make, and decide what global policies we need to standardize. I mean, not everything needs to be standardized. We don't need to standardize how we are modeling listener. That doesn't need to be standardized. That can be left to the people who know listener, registering the listener, perhaps, right? In fact, multiple people can model the listener very differently because they're looking at it from very different angles, right? But we need to standardize what modeling language we're using, how we're semantically or syntactically, what schema language we're using, so we have a consistent experience. And then we need to kind of make sure, as part of the platform, the modeling, if one of our standards modeling, that can be automated, right? So, and that automation can be made available to every single data product, embedded into every data product. So here I have an example of, let's say we want to standardize how each data product expresses its quality metrics. And there is a W3C data quality vocabulary. Let's say we look at that, we like it, we take some of those metrics in terms of completeness, in terms of compliance with existing standards, in terms of quality, integrity, and so on, timeliness, duration, retention, and so on. And then we say, okay, the platform is going to provide libraries in terms of sharing and calculating these qualities. Platform will provide SDKs that the data products can embed and have an API now, have a standard API for exposing those, and the platform will provide the global visibility to that, right? So that's kind of how to think about the computational governance. And if you bring it all together, this is what it will look like. It will have a, you will still have your microservices, your operational plane, you will still have your data plane with your data products, but these are tightly closed together across the domain. And then you have your multiple platform to kind of support it, and your operational kind of computational policies to govern. So where do we get started? How do we get started? This is a lot of work. It's a journey. So, but I would say, if you are thinking about implementation of the data mesh, I love to leave you with this quote from Immanuel Kant, philosopher, that we need to start looking at the whole. We need to see the big picture. Where does this data mesh fits into the bigger picture of organization? Think about this as an organizational transformation, and then of course begin small and iteratively and so on. So let's talk a few words on that. So the bigger picture of an organization, this is a model that ThoughtWorks has implemented, is really evolving around this loop, around this, we'll call it the intelligent enterprise, a cycle of intelligent enterprise, or something along those lines. Sorry if I butchered it. That really starts from, data starts its journey from its points of actions and interactions with applications. We build these data products, we connect them together. But then we start creating maybe higher order insight data products like that, listener profile or recommendation data products. And then we go into building these intelligent solutions and APIs and services that embed that intelligent recommendation into our applications. So if you're changing, implementing data mesh, think about this whole cycle, and then approach a model of transformation that really puts their transformation at the center. This is not a small engineering task that you can kind of sneak in one part of your organization. I wish it was, but it really isn't, because it's about solving the problem of data sharing at an organizational level. Although you might start with one part of your organization, but you still want to understand the bigger picture. So the execution model, I think this is really how ThoughtWorks operates. We love to start with a business and business problem. We want to do that in an iterative fashion and an evolutionary fashion, mature kind of the platforms or the services we build, and make sure our solutions are always end-to-end, every iteration. So what does business-driven mean? That when you get started, first think of in some key business use cases, some intelligent use cases, like, oh, we want to improve our listener outreach, so we need to have our listener profile or something along those lines. Start there, and then identify, okay, what are the domains that I need to have? What are the platform capabilities I need to build? Who are the data users? What's the profile of my data engineer or ML engineer or data scientist? What sort of capabilities do they have, and what sort of platform do I need to build? So one of the workshops that we run goes through this end-to-end iterative execution scenario play. So you, at the center of it, you articulate your use case. What value you're delivering for what customer, through what mechanism, and when you do that, so that you can achieve what outcome. So put that at the center, and then work backwards and say, okay, what sort of ML model or reports I need to generate on the right? Work backwards, okay, what sort of infrastructure I need to place? Work backwards, what sort of data products I need to create? What domains I need to bring these data products to life? What source applications need to be extended to satisfy these data products, source data to this data product, and rinse and repeat. Like, repeat this many times so you build this end-to-end solution. And in terms of evolutionary map, really think about, you're not going to on the day one be where you need to be on 3 years down the track. This is essentially, for large organizations, a multi-year journey. So really be intentional when you're bootstrapping. What sort of business cases you can actually cater, what number of data products you might have, how do you set up yourself? You may set up yourself when you day one a bit more centrally, so you will have a cross-functional team from both infrastructure team and multiple domains, and the users of those domains, the data scientists, the data product developers, the platform developers, all together. But then as you grow your solution, then you kind of start having separate teams, right? Initially, your platform might be fairly opinionated in what sort of services they provide. They're not going to provide all kinds of different services. They're going to look at the population of the use cases and domains and say, okay, well, maybe initially we just provide SQL access, or initially we provide SQL and Parquet, but we're not going to do events. We'll do events later, right? So just like figure out what the platform's opinion is initially. And as you then grow to scale, then you become maybe less opinionated and give access to those very granular utility layer functions as well for more advanced teams. Your teams become completely distributed. Maybe you need to do less hand-holding. In terms of your team structure, I think the adopting and inspiring from the work of folks who wrote the team topologies work is very applicable here. So, you will have this jumped around. You will have this platform team, which essentially inside it's multiple teams, but let's say at a macro level, you have team infrastructure people that are working on just this cross-domain agnostic capabilities, as self-serve capabilities. You will have your cross-functional teams, now your application team, your domain teams, having new streams or new responsibilities for end-to-end and long-term responsibilities for providing their domain data as a product. And you might have a few like complicated systems, like, well, encryption is a hard one. We're going to put a small team to solve that particular problem. And then you might have this kind of enabler teams that work across different streams, help them with adopting the platform, helping the platform with understanding the needs of those domains, and they go across, collaborate across. If you want to learn more, well, I gave you the books, references. There's also the website that ThoughtWorks has, and you can access some content there. Well, thank you. I think I'll leave you with this quote. That this transformation is really a journey, and every journey starts with a single step. And I think you've taken the first step and coming to my talk. Thank you.